So what we see here is we have an aldehyde, and over here we have a Grignard. And what's going to happen is the negatively charged carbon is going to attack our aldehyde carbon of the carbonyl, and we're going to produce an alcohol out of this. So in review, when we see a secondary alcohol, we can say that it came from an aldehyde reacting with a Grignard reagent. It is a secondary ROH. So what we're going to do is backtrack this thing back to the aldehyde it came from, and CHO is an abbreviation for aldehyde, and there is my starting material. In the next one, we see that there's a group 1 metal next to this carbon here. That tells me that this carbon is negatively charged, so therefore that negatively charged carbon will attack my ketone, right? And we know that if I take a ketone and react it with a nucleophile, instead of getting a secondary alcohol, I should get a tertiary alcohol. And what added was this C triple bond CH. Here we have the aldehyde, but here we have Wittig reagent. So therefore I'm going to form a carbon-carbon double bond between the carbon group that's here and my aldehyde. So the next one we have formaldehyde and a lithium reagent, and this is a nice way of doing a 1 carbon extension because C6H5 is nothing more than a benzene ring. And what that reacted with was the formaldehyde, which gives you CH, H, and then OH. So here we see, only because this is a 1 carbon aldehyde do we get a primary alcohol. All other aldehydes will give you a secondary alcohol. And we have a ketone reacting with an alcohol under acidic conditions. It's actually acidic catalysis, acetal formation. We're going to get OCH3 and OCH3. Here we have a ketone and we have a diol under acidic conditions. This is a way of protecting ketones. That diol is going to form a cyclic acetal, which looks something like that. Here we have a ketone reacting with some amine derivative. Remember, if this is an amine, we're going to get this thing to become an imine, and then what we're going to have is a double bond coming off of it, and then that's going to be bound to my nitrogen, which is bound to the R group, and this is called imine. Balance a Tollens reaction and a 2,4-DNP reaction. Remember, 2,4-DNP stands for 2,4-dinitrophenylhydrazine. First we'll do the Tollens reaction. We have a aldehyde who reacts with the ammoniacal silver here in the presence of base. So this is the ammoniacal silver nitrate in the presence of base. And what it produces is silver, or a silver mirror on the test tube, remember, and the oxidized aldehyde to the carboxylate anion. We also produce ammonia and water in the process. This is a positive test, remember, for aldehyde. The bottom reaction is for aldehyde or ketone, where we have the 2,4-dinitrophenylhydrazine, and this forms something called hydrazone. Wait a minute, we have an ester here, which is an acid derivative, and we have a ketone, and we're using NABH4. And if we're using those function groups and NABH4, we know that NABH4 will only reduce ketones and aldehydes, so we'll put our reduced ketone, but realize that the ester does not get reduced. This on the top, the zinc, Hg, and HCl, is called a Clemmensen reduction. The bottom is called a Wolff-Kishner reduction. Remember, the difference in the two is one is under acidic conditions, one is under basic conditions. The bottom line here is, though, you reduce off that C double bond O. And what we're going to now have coming off that benzene ring is a new CH2 between the CH2-CH3, the ethyl group, and the ring. So this is what my C double bond O is reduced down to. Here we have methyl magnesium bromide, CH3 MgBr. It's a Grignard reagent. If I react this with the CO2 in the first step, what I get is CH3, C double bond O, O minus, and then take that carboxyl anion, react it with H3O plus, and what you're going to get is CH3, C double bond O, OH. Benzoic acid, this should look real familiar. We just did this in lab this week, right? C double bond O, O, CH3. This is Fischer esterification. We have the formation of the acid chloride, and we can get from the acid chloride up to the ester by just dumping in CH3OH. This is a large, bulky reducing agent. Notice it only has one hydrogen available, but what you get is the conversion from acid chloride to aldehyde. In the same respect, in the next one here, you can take an acid chloride and get to the ketone instead. Down here, another way we could do this is K2Cr2O7 in the presence of H2SO4, and it's a way of oxidizing primary alcohols to the carboxylic acid. Over here, this goes back to organic 1, taking a cycloalkene or any alkene, and if we react it with permanganate, it cleaves the double bond in half, so we get oxidation on both sides to the carboxylic acid. This one, we have a nitrile in the presence of sulfuric acid, and what that's going to do is take the nitrile and hydrolyze it to the carboxylic acid. So we have aldehydes, ketones, carboxylic acid. This says proton NMR, and so we're going to put 1H down here, and we're going to put 13C, and we'll put IR. If we have RCO2H, then we have RC double bond OH, and the lowest man on the totem pole is always the ketone. Proton NMR, remember the acid, usually around 10 to 12, but the aldehyde is between 9 and 10. C13, around 165 for the acid, 190 to 220 for the aldehyde and the ketone. So you see we can differentiate now, because the acid shows the peak between 10 and 12, the aldehyde between 9 and 10. If you don't see either of these, but you still have a C double bond O in this region here, 190 to 220, you're looking at a ketone. In the IR, remember this shows a large OH stretch, right? And the aldehyde usually shows two peaks at 2800. Ketone, nothing major except for C double bond O.